Hello. In part 1, I shared 3 ways a perfectly healthy model can fail in production: silent data source failure, pipeline sprawl, and observability blindness. If you haven't watched that yet, link is in the description. In this video, we are covering the final two failure modes, both of which hit closer to the model itself, plus a pre-deployment checklist you can use before your next model goes live. Let's get into it. If you're new here, I'm Piyush, a senior ML engineer with 15 years of experience building and breaking ML systems in production. This is part 2 of a two-part series on how perfectly healthy ML models fail in production. And none of it has anything to do with your algorithm. Let's get into it. Data quality shock. That's our next failure mode. What it is? Data quality shock is what happens when your model meets real world data for the first time. It was trained on clean, curated, static data. Production feeds it something completely different, and the model has no way to tell you it's struggling. How it killed us? We trained our forecasting models on CSV exports, clean, well structured, every column accounted for. Before going live, we validated against a held out evaluation set from the same CSV. Metrics looked great, we were confident. Then we integrated live data in production. The outputs started falling outside the range we had seen during evaluation. Not dramatically wrong, consistently off in a way that didn't match our validation results. When we dug in, we found three problems stacked on top of each other. First, schema mismatch. The live data source had columns in different formats than what the model was trained on. Things that were integers in training were strings in production. Date formats were inconsistent. Second, unseen categories. Our categorical features had been encoded based on the training CSV. Production data had new category values we had never seen, and the model had no idea what to do with them. Third, NaN values or missing values. Production data had missing values in columns that were always populated in training. The model had never learned to handle nulls because it had never seen one. Each issue alone would have been manageable, all three together in a live system with business decisions depending on the output. That was the real shock. This happens because training data and the production data are almost never the same thing, and we rarely validate that assumption before going live. CSV exports are snapshots, they are cleaned, filtered, and often manually curated. Production data is live, it has edge cases, late arrivals, format variations, and missing values that nobody thought to handle because nobody thought they would exist. The model learns the rules of the training world. Production plays by completely different rules. How did we fix it? The immediate fix was pragmatic. We retrained directly on the live data that addressed the schema mismatch, exposed the model to real category distributions, and forced us to build explicit NaN handling into the pre-processing layer. But the proper fix came later, a data validation layer built directly into our data engineering pipeline. Here's how it works now. Raw data is fetched from multiple sources, consolidated into a single table, validated, feature engineering runs, final inference ready data is stored. That validation step is the gate. Schema must match, categories must be within known bounds, null rates must be within acceptable thresholds. If anything fails, the pipeline stops immediately, loudly, with a clear error, rather than letting bad data silently reach the model. The fail fast approach gives our data scientists time to investigate root causes. If it's an infrastructure issue, we fix it on the MLOps side. Either way, the model never sees data it wasn't designed to handle. Data quality shock is about what goes into your model. The next failure mode is subtle. It's about the gap between how your model learned and how it's being used. That's the training serving skew. So, what is training serving skew? It is the gap between the world your model was trained in and the world it's asked to serve. Everything looks correct, same model, same code, but the data your model sees at inference time is subtly, structurally different from what it learned from, and that gap silently kills performance. So, how it affected us? We hit this in two distinct ways. The first was missing features. Some features that were present in our training CSV simply didn't exist in live data pipeline. The model had learned to rely on them. They were part of how it understood the problem. In production, they were gone. We had to retrain on live data features, only using what production could actually provide. But more importantly, we built this into our data validation layer going forward. It, if a critical feature is missing from the consolidated raw data, the pipeline fails fast. If it's a non-critical feature, we handle it gracefully, imputing or defaulting rather than letting it silently degrade the output. The second was more subtle, aggregation mismatch. Our training data had a large number of rows representing historical patterns across many time periods. But at inference time, we are passing a much smaller slice of data, just what's needed for the current prediction. The aggregations computed on training data, means distributions, rolling statistics, looked completely different when computed on inference data. The model was essentially seeing a different statistical world than one it was trained on. We fixed this by monitoring the distribution of inference data against training baselines. If the distribution shifts beyond defined thresholds, it's a signal, not a crash, a signal for our data scientists to assess whether the new data represents a genuine change in the underlying pattern. Depending on the valuation, they either retrain the existing model on newer data or build a new model from scratch. The distribution check is what tells us when to act. Training serving skew happens because training and serving are built by different people at different times with different constraints. Training pipelines are built for completeness, all historical data, all features, maximum context. Serving pipelines are built for speed, minimal data, real time constraints, only what's available right now. Nobody sits down and says, let's make these inconsistent. It happens gradually through independent decisions made without a shared contract between the two pipelines. How we fixed it? Two fixes, one reactive, one proactive. Reactive, retrain on what production can actually provide. Stop building models that depend on features your serving pipeline can never deliver. Proactive, we built a distribution monitoring pipeline that runs weekly. Our data engineering pipeline computes the distributions of important features, missing value rates, category frequencies, statistical distributions for each model and stores them in Azure Cosmos DB. A Power BI dashboard sits on top of that, one view per model, one plot per important feature, with threshold limits drawn directly on the chart. When a distribution crosses a threshold, it's immediately visible to the team. That's the signal for our data scientists to assess, is this genuine concept drift, a data quality issue upstream, a seasonal pattern? Depending on the evaluation against the validation set, they either retrain the existing model on newer data or build a new model from scratch. The key principle: the system detects, humans decide. Automated retraining without human judgment is how you silently deploy a worse model. So, we have seen five failure modes, none of them your model, all of them the system around it. Before I close, I want to leave you with something practical, a pre deployment checklist that would have caught every single one of those before they hit production. Before your next model goes live, run through these five checks, one for each failure mode. we have covered. First is data freshness. Does every external data source have a freshness validation? If an API hasn't updated within its expected window, does your pipeline alert? Not crash, but an alert. Next is pipeline consolidation. If you have multiple models sharing similar features, are they sharing code or copying it? One change should require one deployment, not three. Next, step level observability. Does every step in your inference pipeline have a log entry? Data fetch, feature engineering, model call, output validation, database write. Each one should be traceable. Next one is data quality validation. Does your pipeline validation schema, categories, and null rates before data reaches the model? Fail fast on bad data. Don't let it silently degrade your outputs. Last one, distribution monitoring. Are you tracking the distribution of inference data against training baselines? When distributions shift beyond thresholds, your team should know before your users do. 5 checks. If you can answer yes to all 5 before deploying, you have addressed the most common ways production ML systems fail silently. None of these require a new tool. Most require a single engineering decision made before you ship. So let's recap. 5 failure modes, none of them your model. Silent data source failure, your pipeline is too resilient, stale data flows through undetected. Pipeline sprawl, duplicated code, multiplied risk. Observability blindness, no logs means no answers when things break. Data quality shock, production data plays by completely different rules than your training CSV. Training serving skew, the system detects, human decide. If this two-part series saved you even one production incident, that's the goal. Now, in the next video, we are going hands-on. No more slides, no more theory. I'm going to show you exactly how to build a data freshness validation layer in Python from scratch. The actual fix for silent data failure, the first problem we covered in part 1. You'll be able to implement it in your own pipeline the same day. 2 questions before you go. Which of these 5 have you hit in production and which one surprised you most? Drop it in the comments. I read everyone. If you want real AI engineering content, no textbooks, no toy examples, just production war stories and working code, subscribe. New video every Thursday. See you next week.